All right, in this section, we're talking about parametric surfaces, and I think it's going to be a really good idea if you can graph these parametric surfaces, play around with some sort of software that you can get your hands on to do this. Somebody has created a little applet on GeoGebra that works really well. And then if you have Grapher on Mac, that's what I'll be doing in this lecture. That works really well to visualize these things as well. And then let me go ahead and, before I tell you what parameterized surfaces are, let me review some types of functions and the geometric objects that they represent that we've seen so far. So like in Calc 1, we're mainly focusing on one variable functions, and we remember that one variable functions can represent curves in 2 dimensions. So y equals f of x, very familiar. Okay, so a function like y equals f of x, of course, represents some sort of function that looks like this. And that is a one-dimensional curve graphed in 2 dimensions, right? Well, there are other one-dimensional curves in 2 dimensions that you can represent with an equation that isn't necessarily a y equals f of x equation or x equals f of y equation. For example, a circle is given implicitly, x squared plus y squared equals 1, something like that, right? And then we've also seen one-dimensional curves in 2 dimensions represented parametrically. So not only do you get a geometric sense of an object, but also a sort of motion imposed on it by the parameter. So you could parameterize a circle, for example, using cosine and sine in the x and y variables. And that not only gives you a circle, but it gives you a rotation about the circle. But in any case, these 3 distinct ways of expressing a function all express the same type of geometric object, at least dimension-wise. They describe one-dimensional curves in 2 dimensions. All right, let's think about surfaces, 2-dimensional surfaces in 3 dimensions. Well, those would be given by 2 variable functions, fx, y. That's sort of where we started the course, right? They could be given implicitly, like our quadric surfaces or something. So a 3-variable function set equal to 0. So like imagine a sphere, x squared plus y squared plus z squared equals 4. That is a surface given in 3 dimensions, given implicitly. And then finally, in parametric form, that's what the topic of this section is. So to represent a 2-dimensional object, you're going to need 2 parameters, kind of like representing a 1-dimensional curve requires 1 parameter. So this is our sort of last alternative to these 2 expressions to represent a 2D surface in 3 dimensions. Okay, so how will this look? Well, you are expressing an object in 3 dimensions, so the points specified on that surface are going to have x, y, and z components, and each of those components depend on the 2 parameters. So your x component depends on u and v, y component as well, and z component. Okay, and I just right here in the table, sort of by analogy, you can actually do this in any dimension that you like. We have considered 3 variable functions, and it's awkward geometrically to talk about what they represent, but it can be considered sort of just formally as a 3-dimensional surface embedded in 4 dimensions, whatever 4 dimensions is geometrically, right? An implicit form of a 3D surface in 4 dimensions would be an implicit function set equal to 0, or sorry, a function of 4 variables set equal to 0, so like this. And you could just as easily parameterize a 3-dimensional surface in 4 dimensions. Why not, right? It would just be given then by a vector equation involving 3 parameters. Okay, and I ran out of room, so just understand that in 4 dimensions, you do have 4 components to all your points. So each of those components would depend on the 3 parameters. And this, you can keep going up and up and up through dimensions and define these types of things. Okay, so let's get familiar with how to parameterize some familiar surfaces, and then later we will develop the sort of calculus notions that we're using parametric forms for. And so we call the geometric object that this thing describes a parameterized surface traced by the vector function, and R constitutes a parameterization of the surface. U and V are the parameters, and we call R, which is the domain of the vector field, we call it the parameter space. Okay, so I think the best way to get familiar with parametric surfaces is just to run through some examples. So in this first example, we are trying to find a parameterization of the cylinder of radius 2. Let's make it upright along the z-axis, although we can make cylinders positioned in different directions, but this is a perfectly good place to start. And we want it to have radius 2, so it extends out to 2 here on the y-axis and the x-axis. And we should first remind ourselves how this cylinder is represented using just a Cartesian equation, like when we first encountered cylinders in the beginning of the course. Well, the z variable is free, and the y and x variables are making a circle, right? So x squared plus y squared equals 4 is a circle of radius 2 in the xy plane, and the z variable being free allows it to just stretch up parallel with the z-axis. Okay, so we start there. Now this is the difficult part, and it takes a long time and a lot of practice to get good at parameterizing surfaces. But you'll get the hang of it. I mean, if you kind of remember some standard examples and get really familiar with them, then that'll help you build that skill. So here's how I think about it. I can see that there's like a rotational aspect to the x and the y, right? I mean, x and y coordinates are always bound to the circle x squared plus y squared equals 4. And I know how to parameterize a circle in 2 dimensions. I just do cosine and sine, right? So 2 cosine theta and 2 sine theta. Okay, so that takes care of that in some sense. I'm going to switch to the standard variables that we use in parametric surfaces, the parameters u and v. And so instead of t, I'm going to write u. And it actually is not going to matter if I choose this. I mean, the letter doesn't matter at all, but like I can make this be u or v. I'm just going to let it be u. Okay, so at any given point in time, let's say, the x and y coordinates are following these trigonometric functions. I know that. And then let's think about z. Like, let's say that I'm like identifying a few points on this surface, and I'm looking at their x, y, and z coordinates carefully. Like right here, the x and y coordinates are going to satisfy x squared plus y squared equals 4, right? And so that's going to be a particular value of u that gets it there, like pi over 4, it looks like. And then the z value here is 0. And then if I go right above it, again, I've got x and y determined, let's say, by pi over 4 plugged into these equations. And then z is like 1 or something. And like here z equals 2. So like for every selection of u that gives you an x and y pair, z is going to vary however it wants. I mean, again, z is free in this equation. So I'm actually going to let z be its own complete value. I don't want z to actually depend on u, because u is going to determine a particular place along the circle, and then z is just going to take on every single real number value above and below that. So this is a way to get that cylinder parameterized. I'm going to put bounds on the parameters. It's actually not entirely necessary, but it feels natural to sort of give one rotation in u, and then v, of course, since the cylinder goes up and down infinitely, I'll let just v range in between negative infinity and infinity. And now I have built my vector field. Okay, so the x coordinate is 2 cosine u, the y coordinate is 2 sine u, and the z coordinate is v. Oops. Okay, and I want to imagine that, I've got so many variables, right? I've got X, Y, and Z, and then I also have U and V. So let me draw a picture of the UV plane over here for reference. And then, of course, I have the XYZ coordinate system that is acting sort of like as the range of the function, or housing the range of the function. So this expression bounding the parameters looks like the following. Ranging u in between 0 and 2 pi, and then ranging v from negative infinity to positive infinity is like a strip. And this is the parameter space. These are the values of the parameters that go into this vector function, and the output is the cylinder. And we're going to talk more about like sort of what that procedure looks like later geometrically, but just to give you a heads up, moving from the parameter space to the cylinder looks like a wrapping of this parameter space onto the cylinder. But anyway, I want to focus on like building these parameterizations formulaically, and then just through examples exploring that stuff. So let me show you graphically what we got. So I went ahead and graphed this parameterization. So again, I'm using Grapher to do this, and to get the vectors built, you can just choose an XYZ vector, and as you can see here, X is 2 cosine U, Y is 2 sine U, and Z is V, and then I select some appropriate bounds on the parameters. So what I've done is I've also just straight up graphed the usual Cartesian equation of that cylinder, and I'm getting exactly the same image, see? And the software, I guess, treats these inputs a little bit differently, so we're getting a little bit different display on the surface. Sometimes it's useful to go and play around with the settings so that you can see things like grid lines and things we'll talk about later. But anyway, I highly encourage you to use some software to graph the parameterizations that you're building. It's just going to help you, learn the material. Okay, let's go back here then. I want to do another surface. How about the cone z equals root x squared plus y squared? Okay, let me approach this in a couple different ways. And again, you kind of have to be creative, and you pick up on tips and tricks by looking at the different examples in the book and the ones that I'm presenting in these videos. It takes some time, it really does, to get used to this stuff. So take a look at the cone. I still see rotation in the x and the y, right? There's definitely circular stuff happening relative to x and y. So it feels natural to introduce a cosine and a sine here. But notice that, depending on your position on the cone, the amplitude of that rotation is increasing. So it's not like the cylinder above where the x and y coordinates are bound to a specific circle. At any given height, the x and the y coordinates are bound to a different radius circle. And it seems like the radius of that circle is steadily increasing with the z value, right? I mean, you can trace the edge of this cone, and it's a line. So the distance from this line right here to the z-axis seems to be exactly the z value. In fact, you can look at the equation and convince yourself of that. But in any case, I'm going to introduce the other parameter to help increase that amplitude. And again, if I'm not entirely sure that the z is increasing exactly with the radius of that circle, the algebra confirms that for me. If I know I need that amplitude to increase, I slap the v there, and then I can just move up here to the equation, and it will determine what the z has to be. So watch. If I plug in v cosine u for x, I get v squared cosine squared u. And if I plug in v sine u for y, I get this, and then under the radical, this is what the z has to be in order for this parameterization to parameterize the cone. Well, factoring out a v squared and recognizing that cosine squared plus sine squared is 1, we've got the square root of v squared, and here we want the z to be positive, so I'm going to take a square root of v squared and allow v to be positive, all right? So indeed, z has to be v, like this, and I would then restrict v to be greater than or equal to 0 because I only want the top half of the cone. I only want z to be greater or equal to 0. And then u, as before, is going to go through one full rotation, 0 to 2 pi. So there's your parameterization. And I'm also going to draw the parameter space here. So u and v greater than 0 looks like this then, where that red strip is extending to infinity. Okay, so I know that might seem really tricky at first, but as I've been saying, you'll get used to it, you know, as you look at more and more examples. So here's another way that we can parameterize the cone. Instead of using the rotation in x and y to build the parameterization, instead we take the following perspective. What if we just let x and y be the parameters themselves, and since we know exactly how z depends on x and y, we can formulate the correct expression for z from that. So watch how this works. I let x be the u parameter, and I let y be the v parameter, and then I let z be what it should be, which is square root of the x thing squared plus the y thing squared. So that would be square root of u squared plus v squared. Okay, and now in order to find the correct bounds in the parameters, I have to go back to the picture and think about how the u and the v are ranging. So look at the cone. As it opens up infinitely upward and outward, the y coordinate is as positive as you like and is as negative as you like. Same can be said about x. This cone stretches front and back off to infinity and negative infinity. So actually, the two parameters are unbounded. Okay, so when I draw the parameter space for this chosen parameterization, it's actually the entire plane, the entire UV plane, like that. And so there's a couple interesting observations to make, right? Like this parameterization looks completely different than this one formulaically, and the parameter space is different as well. When I take a geometric perspective of how this parameter space parameterizes the cone, like you can imagine sort of wrapping this parameter infinite rectangle onto the cone in a certain way that captures the formulas that we have here, it looks quite different from what how we're sort of wrapping the parameter space here onto the cone. The UV plane is actually exactly the same thing as the XY plane when we set the parameters like this. So the parameter space in this case can be visualized as just sitting underneath the cone itself, and the z being determined in this manner makes the wrapping of the parameter space on the cone just like a lifting of the xy plane onto the cone. And we get another conclusion from this parameterization, and it's the following. Because of the fact that z is a function of x and y, this is always like a really quick and cheap way that we can build a parameterized surface. If z is a function of x and y, go ahead and let x and y be the two parameters, and z's expression will be determined. So I was not able to do that for this previous example because in this case, z was definitely not a function of x and y. In fact, this surface horribly fails the vertical line test, right? But some of our surfaces are functions, and this is always like a quick and dirty parameterization you can construct. For various reasons, you might prefer this other parameterization. Oftentimes when objects have like a round or rotational aspect to them, parameterizing in terms of sines and cosines is preferable. But anyway, these are two perfectly good parameterizations. Let's go ahead and look at the picture. So what I've got here then is the original Cartesian equation of the cone, right? And you can see that the software is automatically putting restrictions on the X and the Y. I haven't imposed any myself. And that's why like it's like selecting, some rectangle of X's and Y's, and that's why we're getting these edges on the top of the cone. But of course, the cone goes on forever upwards. Okay, let's take a look at the first parameterization. So that's this one. I chose the V cosine U, V sine U, and V parameterization to graph here. And you can tell, since the parameters are chosen in this way, it actually prefers a rounded domain on the parameter space. So I chose that. I mean, I allowed U to range from 0 to 2 pi and V, for example, from 0 to 5. That is a circle in the parameter space, right? It's not a circle in the parameter space. It's a rectangle in the parameter space, which imposes a rectangle onto the XY plane, pardon me. So the amount of the surface that has gotten graphed is the circle in the XY plane. Okay, so anyway, that is a verification that this parameterization is legit. It gave us the cone. Here is the other parameterization. So I simply let X and Y be the parameters, and Z is therefore equal to this. And I've given some restriction on those two parameters. And this image looks a lot more similar to the original Cartesian equation. It's because it literally is, I mean, this is just a long-handed way of saying that Z is x squared to x squared plus y squared. But then you can see here that the rectangle in the parameter space is truly a rectangle in the xy plane, which is, the region over which the surface is graphed. Okay, so to summarize, if you have a surface described by a function like this, then to parameterize it, you can do this. Not that. And then range the parameters however you like. So that is building a parameterization RUV, which is U, V, FUV. Okay, now this isn't to say that it's the best parameterization, whatever best is. I mean, as we saw in the previous example, it might be reasonable to use the cosine sine parameterization instead of the function one. And I can give you one idea, like if we're eventually going to integrate over these parameterized surfaces, maybe the expression that results from one parameterization is better than another. And that might be the case if you're parameterizing like a round type of object. You might want to use some more cosine sine type parameterization maybe than like the cheap function parameterization. Like, for example, a sphere, right? I actually don't have the option of a function parameterization in this case because a sphere, wow, that's not very round. Let's try that again. Well, okay. A sphere of radius A isn't actually represented as Z as a function of X and Y, or really any function involving the Cartesian variables like this. So I don't have this parameterization as an option. We know from different coordinate systems that we've studied that like R equals A is sort of the simplest description of the sphere that we have so far. And I'm actually going to use spherical coordinates as an inspiration for when I build the parameterization. So let's remember how spherical coordinates work. You've got the rho variable, right? And then you've got the theta variable and the phi variable. As I mentioned before, I like to think of the phi variable as the latitude and the theta variable as longitude. So just living on the surface of the Earth, I know that latitude and longitude is like a sufficient coordinate system to locate any point on the globe, right? And in a similar way, these two variables, these two parameters really, are sufficient to identify any point on this sphere of radius A, right? So if I use latitude and longitude as my parameter system, then I kind of already know what X, Y, and Z should be in terms of those. If I'm talking about the surface of the sphere rho equals A, then I can set up the spherical coordinates as normal and these will trace out the sphere as I want. So like, this is what I mean. Okay, so there you go. I've written out X, Y, and Z in terms of what they are in spherical coordinates. Of course, setting the rho equals A here allows me not to trace out the entire three-dimensional coordinate system with rho, phi, and theta. I'm just tracing out the surface of rho equals A, which is this sphere right here. So that's clever, right? Let me go ahead and then switch over to the default variables in this chapter. I mean, this isn't necessary, of course, but I'm just emphasizing that we are building these two parametric surfaces. So like this is what it might look like. And then I think about how I need to arrange my longitude and latitude. So U is the latitude variable, and it's going to extend all the way from 0 up at the North Pole down to pi at the South Pole. And then V is acting like theta, that's the longitude, and that ranges from 0 to 2 pi. Okay, so the parameter space here is a rectangle, which was inspired by the phi and theta spherical coordinates. And we have this rectangle, 0 to pi, 0 to 2 pi, and we sort of visualize this parameter space as wrapping around the sphere. And this would sort of be like, you know, if you actually go in the other direction, it's like when you look at a two-dimensional map of the Earth. We do this all the time, right? The latitude and longitude lines are sort of vertical and horizontal, right? And you can imagine that wrapping as you know, transferring this grid onto the longitude and latitude lines that we see on a globe. And then just lastly, let me just write it out as a parametric surface. So what I've built here is the following.